Hello guys, welcome to Sergey's Chemistry. Today's topic is alcohols. And what are alcohols? It's any substance which have OH group attached to saturated carbon. Saturated carbon is any carbon without double bonds around it. So carbon with alkene group, just the same carbon which has OH, wouldn't be an alcohol because the group would affect OH properties. Also, carboxylic acids are not alcohols, though they do have OH group, because their carbon atom has double bonded oxygen attached to it. This again changes drastically the properties. Real alcohols just have carbon chain and OH group attached to that. So what are other substances having OH group? Obviously, first of all, this is a water molecule. Water molecule has OH group. If you look at it, it has even two. So if we compare alcohol and water, we see some similarities, and the difference is that where hydrogen is in case of water, there is alkyl chain or single group in case of alcohol. So we expect some similarities between properties of alcohols and properties of water. And let's list them all, because we know something about water, so it would help us to understand alcohols a little better. First thing, water can form hydrogen bonds, alcohols can form hydrogen bonds. For that, they have everything is needed, because for hydrogen bond you need hydrogen attached to small electronegative atom. Oxygen is here. And what follows from that? Hydrogen bonds mean strong interaction between molecules. So means high boiling point and high melting point also. High boiling point. It's understandable why. And the more OH groups alcohols would have, the higher would be the interaction between molecules and higher would be the boiling point. What else? The next thing which we expect from alcohols, they should be soluble in water, at least the lowest member of the homologous series. So soluble in water. Soluble in water. And how soluble they're going to be? The earliest members, methanol, ethanol, and propanol, they have infinite solubility in water. They are miscible with water in all proportions. It means you would never can prepare saturated solution out of them. However, whatever the quantity of them you add to water, there would be never a separate layer. But butanol already has some solubility. It's not infinitely soluble. 8 grams can be dissolved in 100 grams of water. Why this happens? Obviously, it's expected because alkyl group, alkyl chain, which is non-polar, grows bigger. They can establish only London forces between each other. And London forces or dispersion forces are way weaker than hydrogen bonds, so water would go together establishing hydrogen bonds, and long chain alcohols would go together establishing mainly dispersion forces. So longer members of homologous series with say 7 carbons in the chain, 8 carbons already would be insoluble in water practically. So, can we increase solubility of long chain? Yes, by adding some OH groups, more of them. More OH groups is not a problem, you still remain alcohols. Sugars, they are alcohols, like sucrose. It has almost as many OH groups as there are carbon atoms, a little bit less. But you see solubility of it, and there are 12 sugars, so and there are 12 carbons in the structure. So you see, long chain is no problem if you have enough OH groups to form hydrogen bonds. This would keep things soluble. What else can we bring in? Water is a weak nucleophile, as we know. So we expect ability to be a nucleophile for our alcohols also. How to increase the ability to be nucleophiles for them? Nucleophiles, okay. So they can attack with lone pairs on oxygen, and oxygen is partly negative in both of them, because oxygen is highly, obviously, electronegative, and these bonds are polar. They can attack nucleophilic carbons, carbons with partial positive charge. So you can increase ability of them to be nucleophiles by deprotonating them. If you deprotonate water, you have hydroxide ion left. Hydroxide ion is a very strong nucleophile. If you deprotonate alcohol, you have alk oxide, alkyl group, oxide, hydroxide, hydrogen, oxygen, hydroxide, alkyl, oxygen, alkoxide. If this hydrogen is out and there is negative charge, it becomes a strong nucleophile. And you can understand, yeah, it would add this chain through carbon atom, through oxygen atom to some carbon. If it attacks another alcohol, ether would be formed, two alkyl groups connected by single oxygen. What else? Similar. They both have partly positive hydrogen, and this hydrogen has oxidation state +1. So hydrogen is a very weak oxidizing agent in this case. So we can expect it to be a little bit oxidizing because of partly positive hydrogen. So it's enough oxidizing to react, say, with sodium metal. So sodium is oxidized. When sodium reacts with water, reaction is rather violent. Reaction with alcohols, with ethanol for example, is very moderate and can be used to get rid of excess sodium in laboratory, because sodium sinks to the bottom and doesn't melt, and the reaction is not violent. There is no danger either of explosion or fire of sodium. So okay, now we have some list. So they can form hydrogen bonds, alcohols as well as water. Therefore, we expect them to be to have high boiling points, to be soluble in each other, at least for earliest members of the homologous series. They both are nucleophiles, moderate ones. They have a little bit positive hydrogen, which is moderately oxidizing. So very strong reducing agents, such as metals of the first group, would be able to reduce water and reduce hydrogen in alcohols. Now about nomenclature or the way of naming alcohols. Let's draw some methylbutanes and put OH group at different positions there, and name the molecules which would be formed. So let's put first hydroxyl group at the end of the chain. This would be a primary alcohol, like by usual meaning. Primary carbon to which functional group is attached only to one carbon. So primary, this is a shorthand for that. Let's make secondary like that. Hydrogen, carbon to which hydroxyl group is attached to two other carbons. This would change chemical properties of the substance. And in the third case, let's put OH group here. We have tertiary alcohol. Obviously, there is three carbons which attach to carbon with hydroxyl group. Secondary, tertiary. Now for names. As usual, we find the longest carbon chain. The trick is the longest which has OH group. I don't think you're going to be caught somehow in A-level chemistry checking for this particular property. If there are two competing groups, even one carbon chain is longer than the other which has OH group, you have to choose as a parent name the one which has OH group. But here there is no competition. This is just butane, yeah. How do we call it? 2-methyl-butane 1O. 2-methyl-butane 1O. This one would be, we start naming carbons, so we start numbering carbons, so that hydroxyl group has the lowest number. So we start from here. So methyl group would have number 3, and we have 3-methyl-butane 2O. What about this? Tertiary alcohol, we go from here, 2-methyl-butane 2O. The names I'm going to write here so that you can see, you can look at the notation. Here are the names. We don't write E at the end of the parent chain, that's a slight difference. This one can be put also before the name of the parent chain. Sometimes it's done like that. But I think in high school books normally we put the number of the carbon with hydroxyl group here just before the suffix. So 2-methyl-butane 1O, 3-methyl-butane 2O, 2-methyl-butane 2O. Primary, secondary, tertiary. Let's take some other molecule a bit more complicated and look at it. Say this. So you see, here first we have to find the parent chain. 1, 2, 3, 4, 5, 6, 7. It should be hept, no? Because this one, 1, 2, 3, 4, 5, pent is shorter. But you see, the parent chain is still coming. Hydroxyl group defines the parent chain. So the parent chain is actually 5 carbons, and it should be some pent O, yeah? Pent 1O, obviously. So what is this group? There is 3 carbons, so this is propyl at second. So then what would be the name? 2-propyl-pentane 1O. 2-propyl-pentane 1O. Here is the name. First, second, 1, 2, 3 propane, therefore the group is propyl. 2-propyl-pentane 1O. Now, for a couple of more interesting alcohols, and we just give them names, traditional and standard. So first let's take propane chain with 3 OH groups. What would be the name of this substance? It's some triol, yeah? But it has a pretty common, well-known common name, glycerol. And if we give the name using standard nomenclature, it would be propane 1, 2, 3 triol. Propan 1, 2, 3 triol. 2, 3 triol. As usual, if there are 3 groups, we say tri, 2 di, 4 tetra. Another substance, OH groups attached here. It would be called, a common name is propylene glycol. Propylene glycol. What would be the standard name of this? It would be propan 1, 2 diol. And the last one, ethylene glycol with 2 OH group. So ethylene glycol. And the name, ethane 1,2-diol. Okay, now glycerol is a well-known substance. It's used in a lot of perfume. It is actually edible, so it's used in cooking. And it's also a result of hydrolysis of esters, which are natural esters, which are fats or oils. So all fats or oils are, you see, it's esters formed from this alcohol as a parent. So fatty acids would attach here, forming ester links, and would form all natural oils and fats. Obviously, different fatty acid would give a different name and different property to the resultant ester. Glycerol is very well soluble in water, as you would expect, seeing 3 OH groups, so a lot of hydrogen bonds. It's miscible with water in all proportions. Here, propylene glycol and ethylene glycols. They are famous antifreeze molecules. Glycerol also can be used as an antifreeze. So what they are doing? If mixed with water, they are lowering the freezing point of water to -40 or in certain proportions, with one of them to -60 degrees, which is needed, obviously. You see, you need antifreeze to prevent freezing of water in a cooling system of the engine in countries where temperature drops below 0 Celsius. And why actually they low melting point of water? The thing is that they prevent water from forming perfect structure of ice. If percentage of them is pretty high, around 60%, with 40% of water, you see, water molecules to freeze, they have to form perfect arrangement and perfect structure, so that every molecule of water would form 4 hydrogen bonds with its neighbors. And these alcohols would make these bonds with waters, breaking their proper arrangement, so crystals cannot form. So freezing point of water, in addition of these substances, substantial addition, would drop like pretty significantly to -40, -60. Let's now look at chemical properties of alcohol, or try to predict chemical properties of alcohols looking at its functional group. Here I have primary alcohol for you, and the functional group is OH, but it has also effect on neighboring atoms. So let's discuss it in turns. So first thing, one can expect substitution reaction to take place. Well, but for alcohols it's a particular difficulty, because hydroxyl or hydroxide group, which would happen if hydroxyl would leave. Hydroxide group is bad living group, as we say. Good living group would be water. Bad living group, the stronger nucleophile, the worse the living group is. And hydroxide is a pretty strong nucleophile. It's stronger than, say, chloride ion. So if chloride ion would try to substitute it here, OH group wouldn't live. They would compete for the same carbon, and hydroxyl group would live here, would win the game. So reaction doesn't take place. So what is the way out? Can alcohols actually participate in substitution reactions? Yes, they just need a little help. This group can be converted into good living group just by protonating it with hydrogen ion. This is becoming almost water. H2O plus 1 with breaking this bond heterolytically, it would get this missing electron and leave as water molecule. Water molecule is pretty weak nucleophile and good leaving group therefore. So when alcohols react by substitution, first step is always conversion of OH group into good leaving group, and the simplest way is protonation. Other ways would be to form some complex with oxygen, either with phosphorus or with zinc or with other things which are other reagents or just catalysts. But again, simplest thing, just to make reaction in acidic medium, especially using concentrated acids, and this would become a good leaving group because it will be inevitably protonated. And here I put just, you see oxygen has two lone pairs, they're obviously the same, but I made them of different colors because they have sometimes different meaning in different reactions. So this one on oxygen means that OH group can be protonated and participate in substitution reactions. Alcohol would participate in substitution reactions. What is next? Look at this green hydrogen which I have drawn here. You see, the thing is that oxygen affects carbons which are attached to it. So first of all, oxygen is, as you know, strongly electronegative. Electron density would be withdrawn from this carbon, and these bonds would be unduly polarized. These carbon-hydrogen bonds are much more polarized than these bonds. And somehow, maybe the presence of oxygen also helps. These hydrogens are becoming different one than normal hydrogen in the carbon chain. They are becoming susceptible to oxidation. Or one can say this carbon is susceptible to oxidation. If you look at oxidation number, it's just +1 for each hydrogen. They are not oxidized, but carbon is. So by oxidation I mean that hydrogens would leave and more bonds with oxygen would form. So this carbon would be forming more bonds with oxygen, so would be converted into something like aldehyde or ketone or carboxylic acid. So another thing, oxidation. So alcohols are reducing agents, and we expect them to be, well, actually it's a kind of post factum reasoning. We are trying to explain why they behave like that. So these hydrogens can leave, this carbon is going to be oxidized if there is a strong oxidizing agent nearby. Also I marked with special color this hydrogen here on the carbon which is really far removed from oxygen, and what can affect it? Well, the thing is that if water with protonation of this group is going to leave, the carbocation is almost formed, its formation either taking place, especially for tertiary alcohols or secondary ones, or in primary when it's imminent. What can happen? Hydrogen can be removed by some base passing nearby, and this pair would heterolytically break and goes here. So what would happen? Water would leave OH group and hydrogen, and double bond would be formed here. This reaction is elimination. Actually, it's dehydration, elimination of water from alcohols. So, elimination. It's pretty natural for alcohols reaction, so water would leave, alkenes would be formed. Necessary condition, acidic, strongly acidic, needed for protonation of OH group. Elimination of water, formation of alkenes. Next thing we already discussed, yeah? Hydrogen with partly positive charge. So alcohols react with sodium. making hydrogen gas. And alkoxides. Another thing, this black pair. Black pair means partly negative oxygen, that alcohols are weak but nucleophiles, not worse than water. So they can participate in addition followed by elimination, in formation of esters, in formation of ethers if they, say, attack another alcohol. So I will write here they are nucleophiles. Okay, that's again chemical properties by looking at the group. Next thing would be making a list, not full list obviously, but the list of reactions which are normally mentioned in A-level chemistry in high school, but which are still interesting and are based on the properties of this functional group. So first reaction to discuss logically it would be substitution reactions. When instead of hydroxyl group I would have different halogens. So chlorination can take place. How chlorination can be done? Just with concentrated hydrochloric acid, for example. For tertiary alcohols especially, tertiary reacts faster than secondary and primary. What then? I can create hydrogen halide in situ, just in the place, by reacting potassium chloride and concentrated sulfuric acid. Again, what would happen when I mix these two substances? Hydrogens would join to chlorines, making hydrogen chloride gas, which would escape, creating misty fumes, etc. But if there is alcohols around, a reaction would take place, substitution. Obviously, first thing, you have to protonate this oxygen with the acid, but acid is around. There is a third possibility even, reacting our alcohol with compounds of phosphorus and chlorine. So phosphorus pentachloride, for example. It's actually a universal technique. You can use phosphorus bromides and phosphorus iodides for the substitution, because phosphorus would pair with this oxygen, creating out of hydroxyl a more complex group, which is a good leaving group, and substitution is much facilitated. So this is immediate reaction. For this you would need reflux. This you would easily perform with very reactive, say, tertiary alcohols. But this is immediate, and this is also used as a test. This is also a test for substances having OH group. Phosphorus pentachloride would react with them all. And who are those who have OH group? Alcohols, carboxylic acids, and water. So with all these three, test for OH group. Unfortunately, it's not specific for alcohols, but it's still good that it exists. Misty fumes of hydrogen chloride gas. Why there are misty fumes of hydrogen chloride? As hydrogen chloride is formed, it's very extremely soluble in water, so it will absorb some water from the atmosphere, making tiny droplets of hydrochloric acid, which we see as fume. Yeah, what is fumes? What is mist? Tiny droplets of liquid. So here also tiny droplets of liquids are formed. Simply it's hydrochloric acid, not water. You can still make sure that it's hydrogen chloride, or at least hydrogen bromide or hydrogen iodide, hydrogen halide, by bringing a glass rod dipped in concentrated ammonia solution. You would see white smoke now formed. White smoke means something made of solid particles. So here, say, hydrogen chloride would meet ammonia molecule This is acid, this is base, making ammonium chloride. Ammonium chloride is a solid. Obviously crystals would form. Solid particles in air looks like smoke. So again, there's a way how to chlorinate it, and we have say chlorine, hydrogens, and R group. Yeah, substitution. Now bromination. How can we do it? Similar way as here, we take potassium bromide and we take concentrated sulfuric acid. No, it wouldn't work because concentrated sulfuric acid would oxidize bromides, and bromine would form, and sulfur dioxide would form, and the result would be very messy. So, but if we take, instead of concentrated sulfuric acid, just 50%, we would decrease significantly possibility of it oxidizing bromines, and instead of oxidation, it would just produce again fumes in situ of hydrogen bromide. And hydrogen bromide, as hydrogen chloride in these two cases, would make substitution, and bromoalkane would be formed. What is the second possibility? Well, we can take phosphorus tribromide. Phosphorus tribromide would react, react with alcohols. Again, phosphorus would complex with oxygen to make a good Levene group, and bromoalkane would be formed. So now, what are the possibilities for formation of iodoalkanes? You see, here are three possibilities, here is two. Well, here is logically just one. What it is? I could have used hydrogen iodide, but it's not very stable and not easily available. I can prepare this in place, or I can prepare, say, phosphorus triiodide, which is easier to make. But how? I just take red phosphorus and I take iodine. They would react on heating on the spot, creating phosphorus triiodide, which would perform the same reaction, and iodoalkane would be formed out of alcohol. Let's try to look at mechanism of halogenation of alcohol with hydrogen halides. Let's take generic alcohol and some hydrogen halide. So first step in this reaction would be, because essentially it should be substitution, but hydroxyl group is a bad Levene group, so the first good step would be this, protonate oxygen, creating now potentially a water molecule as a good Levene group, which could split. Here is our halide ion is left. Now, halide ion would attack with lone pair, and it's negatively charged, would attack this carbon, and now we have good Levene group. This bond would break heterolytically, water would leave, and I have halogen alkane and water molecule. That's the generic substitution reaction with hydrogen halides. In case we need full equations for reactions, and definitely sometimes we would need them, so let's try to write out simple substitution ones. Hydrogen chloride plus generic alcohol. What it would make? Substitution. Water molecule would leave. Again, this hydrogen would go here, this would split, would leave as water, and instead halide ion would come. Another way for chlorination is, say, this phosphorus pentachloride. how these would be organized. First, obviously, I expect chloralkane to be formed. And then there is a substance which is called phosphorus trichloride oxide, like that. And then let's see what should be needed. You see, our OH group is should go somewhere. Here. Obviously, I've forgotten that this is a test for presence of OH group. So hydrogen chloride is formed, which is just forming, misty fumes, and it's a test for substances having OH group. If we prepare hydrogen chloride or hydrogen bromide in situ, for example, like that, we have potassium bromide with 50% sulfuric acid with alcohol. Obviously, bromoalkane is formed, and then one hydrogen would go to protonate this to form water. Water would be formed, and then as one hydrogen is left and this potassium ion is kind of abandoned now, you see, potassium hydrogen sulfate, acid salt. If you look at it, is it balanced? Should be balanced, no? Well, I trust it to be balanced. There is still third possibility. Here we use pentachloride, but if we use trichloride or tribromide, okay, let's use triiodide, which is produced in place out of phosphorus and iodine. And our alcohol, what will be formed? First, obviously, substitution and iodalkane, but then what happens with all this? The substance which is formed is called phosphorus acid, H3PO3. It's very different from phosphoric acid. In phosphoric acid, the oxidation state of phosphorus is +5, here it's +3, and the structure is really weird because one hydrogen is attached to phosphorus directly. But still, we have 3 iodines here, so we have to take this 3 times, but this is our alkyl base of alcohol, so alcohol have to be taken 3 times. Does it work now? 3 hydrogens, 3 oxygens, 3 alkyl groups, 1 phosphorus, 3 times iodine. It works. So this is the list of halogenation reactions for alcohols. So directly with H halide, with hydrogen halide, easy substitution, water and halogen alkane. With pentachloride, phosphorus trichloride oxide, and telltale misty fumes of hydrogen chloride gas. Though these hydrogen halides can be made in situ for chlorination and for bromination. So for bromination, potassium bromide is taken and 50% concentrated sulfuric acid. So potassium hydrogen sulfate is formed, water, and our halogen alkane. Another variant of substitution, take phosphorus tribromide or phosphorus triiodide. In case of phosphorus triiodide, it's produced on place, and you have phosphorus acid and iodalkane in this case. Next big group of reaction, it is oxidation of alcohols, and these hydrogen are going to be lost, and more bonds with oxygens would be established. So how this can be done? We just have to use good oxidizing agent. So what is good oxidizing agent? This is potassium dichromate in sulfuric acid. So what is solution of that? So this is strongly oxidizing, and chromium, which is orange here in oxidation state +6, would be changed in oxidation state +3. So orange would turn into green. That's the color change when oxidation would take place. What is the result? There can be actually two results of this oxidation, at least for primary alcohols. Here, primary one, yeah? This is a shorthand to denote primary one. Here I would write what happened to secondary, and here I would write what happened to tertiary. So, tiny one like that. Okay, so now, if I do it under reflux, if I heat the mixture with alcohol under reflux, complete oxidation would take place, all this hydrogen would be removed, and as a result, I would have, okay, I make them in green, I would have completely oxidized primary alcohol, which would turn into carboxylic acid. At the same time, I can distill the product as soon as oxidation starts. You see, one can remove just one hydrogen. One can make this carbon lose just 2 electrons, not 4 electrons like here. What would be the results? The result would be an aldehyde. This is aldehyde functional group. This still, you see, it's first step of oxidation. First, it's alcohol is oxidized to aldehyde, and then almost immediately to carboxylic acid. But aldehyde, you see, it can be distilled because you can, if you look at it, you can see that molecules of aldehydes cannot establish hydrogen bonds between themselves. It means aldehyde would have much smaller boiling point than the parent alcohol. So it would be very volatile at the temperatures of reaction, and it's easy to distill it. If it's done immediately, you can collect aldehyde. If you go on with reaction, especially heating under reflux, you would reach complete oxidation and carboxylic acid would be formed. What about secondary alcohols? In this case, we have what would be the structure? Carbon, 1 hydrogen and 2 alkyl groups attached. So only 1 hydrogen is actually in this compromised position, and only 1 hydrogen can be removed and substituted for the bond with oxygen. So what would be the result? Ketone. These alkyl groups remain instead of OH, though I have double bonded oxygen. So this is the same potassium dichromate with sulfuric acid, heat under reflux, aqueous, solution. So oxidation in one step, because only 1 hydrogen is here to lose. What about tertiary ones? In tertiary, we have 3 alkyl groups attached to the carbon with the hydroxyl group. How it can be oxidized? There is no way that it is oxidized because there is no hydrogens. So in this case, if I try to oxidize it, no reaction. So orange color of potassium dichromate, if I perform this reaction, would remain orange color. Here, orange color would change into green because still a reduction would take place. reduction of dichromate, oxidation of alcohol, therefore. Here, no oxidation of alcohol, no reduction of dichromate, no reaction. Now a few words about oxidation of alcohols. Here I have written sequence for oxidation of primary alcohol. And first thing, let's be sure that they are really oxidized. Let's calculate oxidation states of carbon in this complex, in this, and in this. How we do it? Remember the definition of oxidation state, oxidation number. It's a charge of an ion which would be formed out of carbon. If you break all the covalent bonds, assigning the electron pair to the atom with higher electronegativity. Like here, the pair would be assigned to oxygen, and then our carbon would lose one electron. Plus one here. What about this bond? This bond is with alkyl group. So if this is carbon, so they're equally strongly electronegative, so nothing would happen. The bond would break homolytically if it would ever break. Now here, hydrogen has less electronegativity than carbon, so it would lose the pair to carbon. Carbon would get extra electron here and here. And now let's sum up. -2 plus 1 is -1. That oxidation number of carbon here. In the analogous manner, oxygen oxidizes heme 2 times. Hydrogen gives 1 electron, 0 with another carbon. What is the result? +1. That's oxidation number of carbon here. In carboxylic acid, total oxidation with oxygens and 0 effect on this with carbons, +3. Now see what happens. 2 electrons are lost in the first oxidation from primary alcohol to aldehyde. Another 2 electrons are lost in oxidation of aldehyde to carboxylic acid. Overall, a carbon can lose 4 electrons. You see, oxidation state changes from -1 to +1 to +3. So still, if we are to write a balanced equation for oxidation reaction, what we have to do? Let's start with some generic alcohol and see what can be done here. When it reacts with oxidizing agents such as acidified potassium dichromate, the reaction would be pretty complex, but we go away just saying that it's oxidized, so some oxygens would come and take care of the reaction. Still, we have to balance it. For example, it is oxidized to aldehyde. So, you see, to balance it, I have just to put water molecule here. Now it's balanced. It doesn't give us much sense. These ideas is much more productive, in fact. But still, that's the reaction. If they ask you, write this. What if you have oxidation to carboxylic acid? The same thing. Balance it with oxygens, carboxylic acid, OH, and then you just would need again water molecule to take away 2 hydrogens, and you need twice as much oxygens, I believe. 3 oxygens, 3 hydrogens, R group, it's balanced. So this reaction for oxidation, just use generic oxygen, make sure you form your oxidized substances and some water molecules. Another possibility, dehydration in presence of acids and forming alkenes. And we just draw this. I will put conditions here, but first, what alkene would be here? Just normal one, double bond, H, and there is our new R group because you see I put one hydrogen, I change my one carbon, I change my R group here. So what are conditions? One can do it with concentrated phosphoric acid. It's good because phosphoric acid is non-volatile, so you can heat it up and it wouldn't escape, and it's also non-oxidizing, so it wouldn't oxidize alcohols. Another possibility is heating it with sulfuric acid. Sulfuric acid, though, is oxidizing, though it's also non-volatile. So you have to take care heating it at about 170, 180 degrees, but not more. Then dehydration will take place. One can do it also easily in laboratory setup using aluminium oxide as a catalyst under heating. It will also break down into two molecules, alkene and water. Let's now just write out the mechanism of elimination reaction. First step would be protonation, and second step would be elimination of water. First step here, it's protonation of carboxyl group. So what happens? The pair from oxygen is donated to hydrogen, which is forming covalent bond with it, and bond in acid would break heterolytically, creating conjugate base out of the acid and protonated alcohol, which has now a good leaving group. So next step would involve leaving of this group. This is the second step. As you can see, conjugate base, or maybe it's some other base, for example another non-protonated alcohol, would donate the lone pair to this hydrogen. This group, let's draw it, would donate lone pair to this hydrogen, restoring the acid. Then this bond is going to break heterolytically and form a second pi bond between carbons, and finally water would leave as a good leaving group, and that's basically the end of it. So essentially, what's the result of the reaction? We have in the beginning alcohol and acid. At the end we have alkene, water and acid. You see, acid, we started with it, we ended up with it. Acid is a catalyst here, like phosphoric concentrated or sulfuric concentrated acids. And water. So as a result, these change into this, splitting out water. Elimination of water, dehydration, formation of alkene. Important feature of this reaction is that it's reversible. Each step of it is in fact reversible and can go in both directions depending on conditions. If you want to create elimination, we want to have pressure low, for example. So this can be done at atmospheric pressure. If we want to shift equilibrium to the opposite sides, you see there are several moles of gases here. Acid normally is not gaseous, sulfuric is not volatile, phosphoric is not volatile, so these ones would be two gases at the temperature of the reaction, and here is only one. So increase of pressure would shift equilibrium backwards. What we would have? Hydration of ethenes, creating alcohols. We know this reaction when we studied properties of ethenes. But here, yes, we can drive it in opposite direction at low pressure. these three were the main reactions. So this is substitution and creation of halogen alkanes, oxidation of primary and secondary alcohols, and elimination of water and creation of alkenes. Now just some minor things, some of them are just obvious. So first is the reaction with sodium. When alcohols react with sodium, hydrogen is formed, hydrogen gas, and alk oxide, which is similar to hydroxide. Simply instead of H, there is alkyl group. So alkoxide. So here is sodium alkoxide. So for example, if our alcohol would be ethanol, it would be sodium ethoxide. Sodium ethoxide is ionic and it's very soluble, pretty soluble in ethanol. If we evaporate ethanol, it would be left behind as a white substance. I can reconstitute alcohol back again from it by adding hydrogen ions to it. You see, it would readily accept them. Alkoxides really are good bases. Let's look at detail and try to write an equation for the reaction of ethanol with sodium forming hydrogen gas and compare it to the reaction of sodium with water. So here we have water and here we have ethanol. So you see the difference. Sodium would sink in ethanol. Ethanol has lower density and sodium has actually higher density and sinks. Here, in reaction with water, ethanol would whiz on the surface, actually on the kind of air cushion of hydrogen gas formed. Slightly visible white, leaving slightly visible white trail of sodium hydroxide. So water would react with sodium, making sodium hydroxide. Actually want to make it a bit opposite. Hydroxide, it would be like that. Negative, sodium positive. They would be in solution, obviously, and hydrogen gas is formed. It should be balanced because you see hydrogen, you need two of them, so everything is going to be done twice except for it. So reaction is violent, sodium melts, sodium runs on the surface. Sometimes, especially if you help the reaction a little bit by heating up the water, it can catch fire or can explode. At cold water, when the water is cold, at cold temperature, it never does that. Reaction of ethanol is exactly the same. Simply instead of hydroxide, I have alkoxide. Sodium alkoxide and hydrogen gas. So this reaction is safe, relatively slow, no danger of any explosion of fire of sodium. And this is very useful. You can not use ethanol, you can use any other alcohol with relatively small chains to dispose of sodium. You know, yeah, when we use sodium during experiments, something is left over, you cannot just throw it out and you cannot return it to the bottle as we never do with chemicals. So we have to throw it out somewhere, but it reacts with water in the air, creating sodium hydroxide, which is corrosive. And we cannot throw it just out in the sink because it starts reacting with water, making explosions of fire. So, safe way, put it in ethanol, it would sink, produce sodium ethoxide. What's another thing? Burning. Let's show, which is very obvious. Alcohols burn with clear flame. Why with clear flame? No excess of carbons. there is enough hydrogens there, in contrast to aromatic or unsaturated, for example, substances. And also they have even OH groups as part of their structure, they're partly oxidized, so they burn with clear flame, forming, as you expect, water and carbon dioxide. Another property, and the last one here in the list, would be the reaction exhibiting nucleophilic properties of OH group. This lone pair can be donated to some partly positive carbon, establishing covalent bond and making some leaving group to leave. So, what it can react with? For example, carboxylic acids. So, let's make some arbitrary carboxylic acid, and you see the reaction is lone pair on oxygen would come here, covalent bond would establish oxygen and then alkyl group here, and then one of these oxygens would accumulating enough protons to form water molecule, would split it, and we have ester link behind. Here, that's the ester link, oxygen here, oxygen, carbon, R. That's leftover of our alcohol. This is the one here, attached here. So substances, esters like ethyl ethanoate, propyl butanoate, etc. would be formed. What is another condition here? Sulfuric acid concentrated. Again, water should leave. Now, not from alcohol, but from carboxylic acid. So, concentrated sulfuric acid is needed as a catalyst. I'd like to make an overview of all reactions. So at least these you should know and you should be aware of. So there are three main reactions, this group, and this group. First is substitution and creation of halogen alkanes. OH group leaves as water molecule, and chloro, bromo, and iodoalkanes are formed. So you need either hydrogen chloride, hydrogen bromide, or complexes with phosphorus, phosphorus halides, phosphorus pentachloride, phosphorus tribromide, or phosphorus triiodide, which is made on place in reaction of phosphorus and iodine. So heating under reflux sometimes is needed. Here hydrogen chloride is prepared in place, here hydrogen bromide is prepared in place. So again, hydrogen halides work, yeah, then phosphorus halides work always. Another property, alcohols can be oxidized because these hydrogen are susceptible to oxidation. These bonds are more polarized than normal bonds because of this oxygen withdrawal of electron density. So, acidified potassium dichromate solution on heating would oxidize them. Primary alcohols would change into aldehydes fleetingly, and you can catch this step only when you distill them immediately. Or under reflux, if you continue with oxidation, primary alcohols would be oxidized all down to carboxylic acids. Then, secondary alcohols have only one hydrogen to lose, not two like primary. So it's only one-step oxidation from secondary alcohol to ketone, you see. And tertiary alcohols, as they don't have any hydrogens to lose on carbon with hydroxyl group, they are not oxidized. So orange color of acidified potassium dichromate would change from orange to green for primary and secondary, but wouldn't change and remain orange for tertiary, which would demonstrate that they don't have reducing properties. Another thing, elimination with acids. If I react alcohols with concentrated phosphoric acid or concentrate sulfuric acid but not heating it too much, otherwise sulfuric acid will start oxidizing my alcohols. Water would be eliminated and alkene would be left. So alkenes can be produced in this way. Also, I can do it in the lab by just catalytic breakage of alcohols. Just taking a piece of brick or a pottery. As a catalyst, aluminium oxide is needed, and heating it up strongly, and here allowing the vapors of alcohol to pass over, and then I would collect any gases which would be formed over water, and luckily I would form some alkenes and can test them with bromine water. Bromine water would be decolorized, yeah, from brown to colorless. Another reaction, you can drop sodium in ethanol, it would sink and slowly bubble, and it's a great way to dispose of sodium, extra sodium in the laboratory, because otherwise it's too dangerous to leave it behind or too dangerous to react it with water. Reaction is too violent. But there is a smooth and steady reaction with ethanol, which is totally harmless. And then, obviously, ethanols would burn with clear flame, and therefore they are used as fuels sometimes, and especially in countries where there is sugar cane can be grown cheaply. And ethanol, for example, can be made by fermentation. Here, another reaction. Because OH group is nucleophilic, esterification reaction can take place. How to remember all that? How to keep this all in a head? So I myself had a trouble with that, because it's very easy to forget one out of these 6 different reactions. I try to make a rhyme for myself to remember that. So listen to it and try to understand what it means. It goes like that. Substitute with H halides, acids make alkenes, oxidize and aldehydes and ketones come in. Oxygen burns, sodium bubbles, esters you learn, no more troubles. Yep, that's that's the rhyme which serves me well. So again, I can go along around the properties. Substitute with H halides. Hydrogen halides are the main reactants here to create halogen alkanes out of alcohols. Acids make alkenes. Yes, sulfuric acid and phosphoric acid on heating with alcohols would make alkenes, and water would leave. Substitute with H halides, acid make alkenes, oxidize, and aldehydes with ketones come in. Obviously there is carboxylic acid, but I cannot put everything in the rhyme. Oxidize and aldehydes with ketones come in. Oxygen burns, sodium bubbles, esters you learn, no more troubles. I do it again. Substitute with H halides. Acid make alkenes. Oxidize and aldehydes with ketones come in. Oxygen burns, sodium bubbles, esters you learn, no more troubles. For now, that's it. Thank you for watching, please subscribe to the channel and see you next time.